This is the review of Chapter 14, Introduction to Probability. Alright, so the first thing we need to cover is some vocabulary. Probability represents the long-run relative frequency of an event. So if in the long run, when you roll a die, the number 6 comes up 1/6 of the time, then that's the probability of getting a 6. A trial is a single attempt or realization of a random phenomenon. So like rolling the die, that would be a trial. Outcome is the value measured or observed for a single trial or random event. So I got a 6 or I got a 3. Those would be the outcomes. An event is a collection of outcomes of interest. So I could say, for example, what's the probability of the event of getting all evens, of getting an even number? And so when I roll the die, I'm looking at the probability of getting an even, which would be the probability of getting a 2 or a 4 or a 6. Independent events, knowing whether one event occurs does not alter the probability of the other event occurring. So for example, when I roll the die, I got a 6. Does that change my probability of getting a 5 the next time? If it does, because I knew that I got a 6, then they're not independent. But in this case, they should be. The law of large numbers says that the long-run relative frequency of repeated independent events gets closer and closer to the true relative frequency as the number of trials increases. What this means is, let's say you're flipping a coin and the probability of getting heads is 0.5. If you got 4 heads out of 10, that would not be that unusual, but getting 400 heads out of 1,000 tosses would be considerably unusual if the coin is fair and the probability is really 50-50. Even though these are both 40%, 40% out of 10, not so strange, but 40% out of 1,000, we should expect this to be closer to 50% by the time we've done many, many trials. Many people mistakenly believe or behave as if something called the law of averages held true. And that is the idea, for example, when you're gambling behavior, people will think, oh, this machine is hot, so I should put more coins in it because it's been winning a lot lately. Or, they're going to say, I'm going to bet on red at the roulette table because red hasn't come up in a long time and it's due now. So that kind of behavior where they're acting as if the roulette wheel or the machine had some kind of memory and events were not independent. That is a fallacy behavior. It's not correct behavior, and it doesn't follow true probability with these random events that have no relation to one another. They're independent. So the probability of getting a red is not influenced by the fact that you haven't gotten a red in 10 times. Okay. Some notation and rules for probability that you need to know. We use capital P to represent probability, and then we put parentheses and whatever it is you want to find the probability of. So P parentheses 6 parentheses, that might refer to, for example, the probability of rolling a 6 on a die. Probabilities, when written as decimals, are always between 0 and 1. If you have more than 1, somehow there's a mistake, right? S is a sample space notation, and sample space is the set of all events that can occur. So the sample space for rolling a die is 1, 2, 3, 4, 5, 6. The sample space for rolling 2 die and recording the sums, then you might want to use a diagram to help you find that. Make a chart with 1, 2, 3, 4, 5, 6 across the top for the first die, 1, 2, 3, 4, 5, 6 down the side for the second die, and then fill the chart with all the sums, because there's 36 different sums there. Or maybe if we're talking about tossing a coin 5 times, you could make a tree diagram, heads, tails for the first toss, and then off of each of those branches, heads, tails for all the other tosses. And so that you could find the sample space of all the different outcomes that could happen in 5 tosses. The complement rule is a very handy rule. It says that the probability of an event happening is 1 minus the probability of anything else happening. Main reason why we want to know the complement rule is sometimes finding the probability of an event happening is pretty difficult, but finding the probability of anything else happening, or in other words, that event not happening, is sometimes much easier to calculate. And so that's when the complement rule will come in very handy. The capital U looking symbol, it doesn't have the little tail on it ever, represents union. So you might see it written like this: the probability of A union B, where A and B are 2 different events. That represents the probability of A or B happening in a single event. And that's calculated by adding the probabilities. The probability of A plus the probability of B. As long as there's no overlap between A and B, like they can't happen at the same time. Disjoint and mutually exclusive. Events that have no overlap are called disjoint or mutually exclusive. So these two words are synonyms, two phrases. Think a Venn diagram with circles that have no outcomes in common, so the circles don't overlap at all. For example, rolling a die and tossing a coin. If you were to draw the circles and put every event that could happen in those, there's no overlap because there's no events that have the same outcome between the two. Now an upside down U is the symbol for intersection. So the probability of A intersection B, that means the probability of A and B happening in two concurrent or consecutive trials. And you get that by multiplying probability of A times probability of B. Let's do some problems as an example. So the American Red Cross says 45% of Americans have type O blood, 40% type A, 11% type B, and the rest type AB. What is the probability that a donor has type AB? So basically we know that if we have everything that can happen, all the probabilities when written as decimals need to add up to 1 because that would be the entire sample space. So we can do 1 minus all these other guys to find the probability of type AB. So 1 minus 0.45, that's the type O, and then I think we had 0.4 and 0.11. And that leaves 4% of the population as type AB. Okay? Let's make that red. All right, and then what's the probability that a donor has type A or B? So basically that means either one is considered a success, and so we just need to add those two probabilities up. So 40% and 11% is 55%, or 0.55. Wait, what am I saying? 40% plus 11% is 51%. There we go. Is not type O, and so we know that type O is 45%. What we could do is we could add up type A, type B, and type AB, or we could just do 1 minus the, 100% minus the 45%, or 1 minus 0.45 using that complement rule. Hopefully you can do that in your head. 1 minus 0.45 is 0.55, right? Let's make that red though. There we go. Now what if we have several donors in line? That's where we might get into these intersection questions. All right. So if there are 4 donors waiting to donate, what is the probability that all are type O? So we have 4 type O's, so that's going to be 0.45 times 0.45. Whoops, that did not come out the way I wanted there. Times 0.45 times 0.45 times 0.45, or I might just do 0.45 to the 4th on my calculator. Either way, we get about 4% or so. So approximately 4%. What is the probability that none are type B? So if none of them are type AB, type AB, that means that the first one isn't, the second one isn't, the third one isn't, and the fourth one is not. And so if the probability of being type AB is 0.04, the probability of not being type AB would be 1 minus that, which would be 0.96. And so I want all 4 of them to be not AB. So that's 0.96 to the 4th, or 0.96 times itself 4 times, either way. And so that's about roughly 0.85. Okay, so 85% that nobody of the 4 is type AB. What's the probability that they're not all type A? Okay, so all type A would mean that every single one of them was type A. So that would be 0.4, 0.4, 0.4, 0.4. But I want them to not all be type A. That means maybe none of them are, or maybe one of them is, or maybe 2 of them are, or maybe 3 of them are, but just not all of them. So this is a case where I really want to use the complement rule because I don't want to add all of those different probabilities up. I don't want to have to do the probability of none plus the probability of 1, which is actually pretty hard to complicate because I have to do a combination there because I have to do all the different ways that you could have one person be type A out of the 4. And then all the different ways that you could have 2 of the 4. And then all the ways that you could have 3 of the 4 be type A. So that's just a lot of work. So it's going to be much easier to do the complement that 1 minus all of them being type A. So 1 minus 0.4 to the 4th. And so this is the probability of anything else happening besides all type A. So 0.9744. And so since that was pretty close to the middle of a decimal point, I'm just going to keep one more decimal place there. All right, what's the probability that at least one person is type B? Okay, so at least one means it could be one person is type B, or 2, or 3, or 4. Again, that's a lot of work to calculate because for one person to be type B, I would have to do, 1 type B, 3 not type Bs, and then all the combinations of how that could happen. Plus 2 type Bs. So 2 type Bs, 2 not type Bs, times the number of combinations. Plus 3 type Bs, 1 not type B, times the number of combinations. So again, using the complement rule would be easier here. I can do 1 minus that nobody is type B, because that's the opposite of at least 1, right? At least 1 is 1, 2, 3, or 4, and the opposite of that is none. So I'm going to do 1 minus nobody being type B. So if type B is 11%, and we want not type B, so that's 1 minus 11% or 89%, right? And so I'm wanting 4 of those. So I'm doing 1 minus that we have nobody being type B. And so that's about 0.372. So if you start to find any of these problems difficult, what you might start doing to help you get, figure things out, when you have like these multiple people in line, ask yourself, okay, so what is the first person? What is the second person? What is the third? What is the fourth? If you can break it down that way, sometimes that helps you figure out, what probabilities do you need to multiply. So that's kind of how I was thinking when, they are not all type A. So I'm saying, okay, so what does the first person have to be? Well, if they're not all type A, well, that first person could be type A, but not necessarily. And so then I'm thinking, oh, well, maybe I want to use a complement rule. Is that possible here? Well, not all type A. So the opposite of all type A, not all type A, would be that they are all type A. And so then I can go from there. Same thing with at least one person is type B. So what does that mean? Well, 1 of them or 2 of them or 3 of them or 4 of them. Complement rule comes to mind then, because that sounds pretty complicated. And so the opposite of at least one person being type B is that none of them are type B. So I need to find the probability of not type B and do 4 of those. Okay, so breaking it down into what's happening with each person sometimes, or each trial, sometimes makes it a little bit easier to figure out. So those are the types of probability questions that we saw in Chapter 14. There is some other types of probability that we need to talk about still in Chapter 15, and then on to random variables in Chapter 16. But that concludes the review of Chapter 14.